So I put this talk together as a part of an outreach event a few years ago. I've expanded it and gave it for the Mamaroneck Library a couple of months ago, and I was asked to give it for the club. This is one of those talks that you don't know where to stop because everything is so fascinating and is so interesting that you just keep adding and adding and adding details and facts and images. But I tried to keep it down. It'll run hopefully 90 minutes, maybe a little bit longer, but I think you should be interested all the way through. And certainly some of the images that our club members have produced and also that are produced by professional astronomers are really quite remarkable. So we'll begin with what happens at night, which is first that the sun goes down. But that's not actually the most interesting part of what happens right after dusk or also just before dawn. And a lot of people only focus on the beautiful red sunset. But if you turn around and look the other way, and I'm sure all of you have, uh, you'll see something, and you may not remark on it because you just don't pay attention. And I didn't even know this until about 15 seconds before I took this photograph on a tour of Kitt Peak, and our docent pointed out this kind of reddish band over a darker blue above the horizon and the lighter blue of the fading daytime sky. And I love this quote from Scandal in Bohemia: "You see, but you do not observe." And by the way, that's a great line to use when you're teaching medical students and residents when they see things but don't really know what they mean. You can see this phenomenon just before sunrise, and it's always opposite the sun. Or you can see it opposite the sun at sunset, and you know it's opposite the sun because here's the nearly full moon rising above it. A dark blue, a reddish band, and above it. And this is called the belt of Venus. And it's caused by the fact that the sun is below the horizon and it casts a shadow. And what you're seeing is the shadow of the Earth. And above it, some backscattered sunlight that gives the red band. It's not clear who first called it the belt of Venus, but it is called that because Venus, besides being the goddess of love and the most beautiful woman in the world, uh, had a garment that had this sash on it, and the sash would make men completely drool and completely helpless. And in the Iliad, she lends it to Hera, who uses it to seduce Zeus. And while they're doing it, she arranges for Poseidon to go out and help the Greeks at the Battle of Troy. It's in Book 14 of the Iliad. So this is low down in the atmosphere, but going up a little higher, if you're in the right place at the right time, you can see the Aurora Borealis. The aurora is caused by charged particles that come from the sun. They interact with the Earth's magnetic field, and they can't get directly through. They have to follow the magnetic lines, and so they will impact the atmosphere around the poles. And you can actually get a prediction map by going to the NOAA Space Weather Prediction Center, and you'll see predictions for your area, as well as a map showing what's coming in the next couple of days. And you can see that it's in the northern hemisphere around the poles, around the geomagnetic pole, which right now is up here in the tip of Baffin Island. And there's also a map for the southern hemisphere, but most of those auroras are down in Antarctica where they're much harder to get to. Iceland often is a place where you can go to see it, also in northern Scandinavia, and sometimes around Hudson's Bay or Alaska. The aurora is a changeable display, and it can be extremely exciting, and also it's sometimes extremely cold, and a lot of the good aurora trips take place in February up to northern Finland or Canada's Hudson Bay. So the tour operators will give you warm garments to wear. It can be very bright. Sometimes it can just be very subtle. It's usually green and sometimes a little bit red. That comes from the oxygen atoms that are excited by the charged particles that are moving out of the sun at about 1,000,000 miles an hour. The sun is increasing its activity over the next couple of years. So there may be some coronal mass ejections that'll give us good auroras, peaking probably around 2025. Further up in the atmosphere, individual meteors can be seen almost any night when it's dark and clear. And these are some actual meteor photographs. That's a good one, but sometimes they're very fleeting and you just catch a little bleep like that, and that's all you see. But sometimes, fortunately not that often, the meteors can be very large. This is the Chelyabinsk Fireball that was estimated to be 66 feet long, and it came in about 40,000 miles an hour. It weighed 13,000 tons. It exploded at 18.5 miles above the atmosphere with a force of about 500 kilotons of TNT, about 30 Hiroshimas. And a short time after it exploded, when the speed of sound got the sound of the explosion back down to Earth, it did this.
А что думаешь, может, спутник там уже же падал, они...
There were 1,500 people injured, 7,200 buildings damaged. The largest fragment of this chondrite weighed 1,442 pounds and was fished out from this hole in the ice. A 3 by 2 inch cut slice of this meteorite just sold in March at Christie's, in February rather, for $9,375. Meteors can be very expensive, and some of the really good ones are priced in the hundreds of thousands of dollars. Meteorites come from from planetoids that either formed and broke up, or more likely failed to form early in the history of the solar system. The most common ones are chondrites, and these are the primal dust particles that congealed under gravity and static electricity, but never got heated large enough or got heated enough to form actual planets or planetoids. When they get large enough, the center heats up, the iron goes to the center, and when the planet finally breaks up due to collisions in the early solar system, you get these iron meteorites with the fusion crust on the outside, and the Widman, whoops, that shouldn't have gone. Let me go a page up. And this Widmanstätten pattern that's in the cut section of the meteorite. In space, they're called meteoroids. In the atmosphere, they're meteors, and on the ground, they're meteorites. So make sure when you talk about them, you give them the right nomenclature. This is actually, I own this meteorite, and it's about the size of a biscotti, and it's solid iron, and it's just a delight to hold something in your hand that's 4.6 billion years old. Meteor showers, however, come from comets. When the Earth passes through the orbit of one of the periodic comets in the solar system, for example, the Leonids in November come from comet 55P Tempel-Tuttle. And when you get that, the meteors appear to all be coming, or most of them coming, from an area in space, which we call the radiant, and it's named for the constellation that it's in. These are the meteor showers that happened this year. They're best seen when the moon is not in the sky, and very often the moon is in the sky, so some of the good ones, like the Leonids and Geminids this year, won't be that easy to see. But the Perseids in August should have a good apparition this year, because the moon is, it's a new moon, and there should be up to between 50 and 100 meteors per hour. What everybody wants to see is a meteor storm. And there was a very famous one in the United States in November 12th, 1833. And this was actually the beginning of the entire science of I wouldn't say meteorology, but astrophysical meteorology, as meteors flew down by the hundreds of thousands. People went outside. Of course, there were no streetlights. And nobody expected this. They came out, and everybody saw it. It was described as almost being like a blizzard. So one letter said it seemed to rain fire. Everybody wants to see this. Every once in a while, you'll hear a prediction. There might be a storm, and then usually nothing happens. But it is possible that next May, there will be a meteor storm. when we pass through the orbit of comet 73P Schwarzmann-Wachmann 3, because this comet began to break up in 1995 and the pieces have been orbiting around the sun, and we will pass through that orbit on the night of May 30th to 31st next year. And here's an image from the Spitzer Space Telescope showing the fragments of the comet. And comets often do break up. You may remember the comet that crashed into Jupiter in 1994. The estimate could be up to 100,000 per hour, rivaling the Leonids. It'll be visible across North America, and it's a new moon, so it'll be an optimum time to take your chance. But it's always a chance because it could also be a complete bust. Nothing at all could happen. But people who chase meteor showers are going to prepare themselves, probably go out west where it's likely to be better weather, more predictable than in the Northeast. Of course, you can always see satellites every night when it's clear, and unfortunately many more of them than there used to be because of those Starlinks that are up there that do have some problems for professional astronomy and amateur astronomy photographers. But the ISS is often a delightful object to see crossing in a stately manner across the sky. And you can get various apps for yourself, for your iPhone or your Android phone, that'll tell you when it's going to pass over. Will give you alerts, show you maps, and you'll be able to see it usually in the early part of the evening because it's in fairly low Earth orbit. So if the sun is too low below the horizon, it won't be lit up. But usually at the beginning of some of our star parties, we can see it traveling across the sky. Going further out, the next thing we come to is the moon. And I don't have to tell you much about the moon. You've all seen it. Most of you have probably looked at it through telescopes or at least binoculars. The moon has its phases. We tend to look mostly at the first quarter and waxing gibbous moons because these are in a nice position in the sky after dinner. Because the first quarter moon is up there at sunset, halfway up in the sky. The full moon rises at sunset. If you want to see the third quarter moon, you're going to have to get up early in the morning and go out at 2 or 3. So we tend to be most familiar with the moon's face in these positions. The moon orbits in a synodic period of 29.53 days, and that's the time it goes around to be opposite the sun again. The full moon is beautiful when you can get a nice photograph or have it illuminate a nice walk. My wife and I were in Yosemite Valley in 1992 during a full moon, and we had just a magnificent walk in the valley with the high rocks and cliffs lit up by the moon. And we got this picture totally serendipitously when we were in in Naples a couple of years ago, and happened to be just in the right place at the right time. The full moon itself is not the friend of astronomers. We generally don't like it for 2 reasons. The first one is that it's very bright and it tends to blot out the fainter objects that we're interested in seeing with our telescopes. But also that to observe it, there isn't that much to see. As complicated as it might look, there isn't a lot of definition of the various objects on the moon. You can bring that out a little bit when you photograph it because you can use a red filter or a hydrogen alpha filter, as I did in this photograph, to increase the contrast between the darker Marias and the lighter cratered areas. But you can see along the terminator, because this picture was 17 hours after full moon of a supermoon in July, when the moon was fairly close to Earth, you can begin to see the detail of the craters along the edge. And so we like to look at the terminator when it's crossing the face of the moon, generally, again, in those first quarter phases when we're happily fed after dinner and can go out and take a look. As it happens, here are the Apollo landing sites. They're all obviously on the face of the moon facing Earth, so the radio transmissions could be obtained and the TV transmissions. But if you stay up late, you can see the moon in its third quarter, and there's some interesting things to see here. For example, here is the Apennine Mountains the sun is just setting on them, so the peaks are being illuminated, but the body of the mountains are now in darkness. You can also see this little white streak here is the straight wall. We tend to see it as a black streak when it's being lit from the other side, but here it's the face of it is being lit. And I'll show that to you in another photograph in a minute. Here's Copernicus, a crater that everybody likes to photograph, and you'll see one of those too. When you put a telescope on the moon, almost any telescope, even a little 2-inch scope, will give you a nice view of the craters and the details, as long as you look generally fairly close to the terminator. And here we have Tycho, Longomontanus, and Clavius. But all over the moon, it's just fascinating to look at. And there's obviously a lot of craters, a lot of areas where there's kind of ejected from the craters that you can see. Lava flows. Here, this crater probably has had some lava flow into it, and that's why you don't see any detail. Everything's been covered over. Here's Copernicus, and its scalloped walls always make for a nice view. You can see the beginning of the Apennine valleys coming out from the crater Eratosthenes, and here's the crater Kepler. And you can see these streaks. This is the small bits of dust and rock that were ejected when the crater hit the moon. And this crater probably hit about 3.9 billion years ago. So there wasn't anything up there to disturb it until our astronauts started walking around on the moon. You can get a lot of detail. This crater here is only 3 miles wide, and there are even some smaller craters on this photograph, and this is with a fairly small telescope. Here is the straight wall, now lit from the back in the Mare Nubium and the crater Borealis. And you can again see the lava as it's flowed through this Maria, the sea. This is a recent photograph just from a couple of weeks ago with a new camera that I got showing the crater Archimedes and the Apennine Mountains. Here is Mount Huygens, which is the highest mountain on the moon, about 16,500 feet. And you can see these little tracks. These are faults in the moon, and this one is the Rima Bradley that the Apollo 15 landed right about here. Rima Hadley, pardon me. There's a camera on a satellite that's been circulating the moon, around the moon since 2011. The Lunar Reconnaissance Orbiter craft has a camera that's operated by Arizona State University. If you actually get out to Tempe, you can visit the headquarters there and see them actually driving the thing and obtaining images from the moon. Tens of thousands of images have been returned, and they give incredible detail. But they've also imaged all of the landing sites of all of the American and Soviet space probes that have landed, the 6 Apollo probes that were missions that were manned, as well as a bunch of Soviet and earlier American space probes. And you can actually see the footprints, tracks of the astronauts. This is Armstrong walking out here. In that first picture I showed, you can see them planting the flag. That was right about here. And here's the camera that was in the back part of that photograph. And I guess we could use this to try to prove to those naysayers that we actually did go to the moon, although they'll argue that this is fake too. But of course, we did go to the moon. The moon gives us some excitement about once a year. Sometimes twice a year, we can get a lunar eclipse. This occurs during the full moon, when the moon passes into the shadow behind the Earth. And you may ask, why don't we see that every full moon? It would be pretty cool if we did. But in actual fact, the moon is only a half a degree in size in the sky, and the orbit is tilted just over 5 degrees. So most full moons, the moon is either above or below the Earth's shadow, and that's why we don't see a lunar eclipse. When we do have one, though, you can see the shadow of the Earth begin to cross the moon, and you see it's a little bit of a curve, so this is some direct proof that the Earth is round. if you need that to convince any of those flat earthers that are out there, and there seems to be plenty of them. The color of the moon is always some shade of red. It can be fairly dark. Photographs tend to show it a little bit lighter than it really is. This is getting to kind of what it looked like in the last one we had here a couple of years ago. The reason that it's red is because when the sunlight passes through the Earth's atmosphere, the blue wavelengths are scattered, which is why the sky is blue. It's Rayleigh scattering. And the red wavelengths pass through, so they will impinge and land on the moon and make it red. So if you were on the moon and looked at the Earth during an eclipse, this is what you would see, a red band around the moon. I don't think any of our missions were there at a time when that could be done, but someday that'll happen. This is the one daytime event I'm going to talk about. When the moon passes between the Earth and the sun, the moon's shadow sometimes will fall on the Earth. Again, the geometry has to be just right. And you can see from space, here's the ISS, you see the umbra, the direct complete blotting out of the sun, is a small area, usually about 60 miles wide, and then around it is the penumbra, the partial shadow. And it travels across the Earth at 1,000 miles an hour. These eclipses will last a total of a few seconds to about 7 minutes is the longest one that anyone can experience. And these are the most spectacular of all astronomical events. And any of you have seen what, you will know what I mean. I've been able to see 3, and they're really incredible. The one in August, about a quarter of our club actually went out to the center line to see it. We were up in Idaho, and Mike Versinger, a member of our club, was in Illinois and took this photograph. You can see the corona of the sun, and you can see some prominences coming off the limb of the sun. Fortunately, the sun and the moon are just about the same size in space. The moon is 400 times smaller than the sun, but 400 times closer. So fortuitously, they can make these beautiful eclipses once in a while. The moon is moving away from the Earth about 3.8 centimeters a year. And eventually it will be far enough away from the Earth that we'll never get total eclipses again. We'll just have annular eclipses. It's a very exciting event. The moon creeps across the sun, and then all of a sudden the corona pops out. Everybody goes nuts. Even atheists start screaming, "Oh my God, oh my God." And it's really an astonishing event, as those of you who've experienced it know. The moon's shadow doesn't blot out the entire sky because there's sunlight ahead of it and behind it. And you can see that. We were on the Sky and Telescope eclipse flight 2 years ago, and we're up at 37,000 feet, and here's a picture of the eclipse, and you can see the sunlight behind it, and here's the moon's shadow over the Earth. It was a fun flight to be on a 150-seat airplane with just 38 people. And the pilots left the door to the cockpit open so we could go in and out. It was Latam Airlines, and it was really great. Flight out of Santiago. There'll be a total eclipse on April 8th, 2024 that will go right across the United States and will be not that far in upstate New York. The weather prospects are better the further south you go. So there'll be a lot of people coming into Texas and maybe northern Mexico. You have to start planning now. I think every hotel room anywhere near the eclipse path is probably already reserved, at least by tour companies. Partial eclipses, like one we're going to have in a few days, can be interesting, and they can make for very nice photographs. This one of a photograph in November 2013. I actually also took a picture of this one, but I was over in Larchmont Harbor, and we had a lot more clouds than this, so I didn't really get much. But this is kind of a cool photograph. The annular eclipse on the 10th of June is going to be over pretty much the North Pole, and not too many people are going to see it on the ground because it's going to be up in Hudson's Bay and then in Greenland and then eventually in Siberia. But there will be a partial eclipse visible in our area and also down in Europe. But the partial eclipse begins at sunrise, and it will only last for an hour. And this is what it's going to look like about 10 minutes after sunrise, when it'll just be 1 degree above the horizon. So you really need to be able to see over water in that azimuth, about 59 to 60 degrees from north. But this is what it's going to look like. When it rises, just the 2 horns of the sun are going to be above the horizon. And if the weather's good, that'll make a fantastic photograph. But make sure that even a partially eclipsed sun, you can't look at it directly. It's really important to have proper eye shielding, and you can't just use sunglasses. You know, you have to get these special eclipse shades and not do this. And you can get these if you're interested in looking at that eclipse on the 10th. If you order them now, there's a number of different ones available, and they can ship them out from Amazon in a couple of days. There'll be an annular eclipse also that's in a more favorable viewing in October 2023, and this runs across the southwest, and it's usually a good time for weather, so this is probably a good one to see. They're hardly as dramatic as total solar eclipses, but they are interesting phenomena. They occur because sometimes the moon is farther away. It varies by about 50,000 miles between its closest and its farthest points in its orbit. And if the sun happens to be right in line when it's at the apogee, then you'll get a annual eclipse. The Earth rotates on its axis, as you know, and it tilts by 23.5 degrees, which is why we have seasons. And if you made a photograph just pointing at the North Star in a dark place, you'll get these beautiful star trails. And the star Polaris is within 1 degree. It's actually, I think, right now 52 minutes of arc from the true North Pole, and getting closer, it'll be at its closest point around the year 2100. And so stars and constellations rise in the east and set in the west. That's the daily rotation of the Earth. The annular rotation of the Earth around the sun means that the sun is going to pick out a path among the stars and look like it's traveling on the stars to make a complete revolution in 365 days. And the ancients knew where the sun would be and what constellation it would be, because they knew that the sky was a sphere, the inside of a sphere, and functionally it is. And so they created the zodiac and a line called the ecliptic. The ecliptic is the path that the sun takes in its annual trip, through the sky. And the ecliptic is the plane that all the planets are also on. So the entire solar system is essentially on the ecliptic, at least within a few degrees. So the ecliptic itself is a plane, and when it's at its highest point above the Earth's equator, that's the summer solstice, like we'll have on June 21st, and on December 21st, the winter solstice. And the two planes cross in the spring and in the fall when we have the equinoxes. Because the planets are all in the plane of the ecliptic, sometimes they get close together. The moon, too, is within 5 degrees of the ecliptic. So we get conjunctions. And the interesting thing about conjunctions is they remind us of the way in which astronomy and astrology evolved together. Really, astronomy was in service of astrology for the first couple of thousand years of its existence, until astronomy became a truly scientific pursuit in the beginning of the 17th century. It does irk a lot of us when somebody says, "Oh, you're interested in astrology," when they meant astronomy, but we tend to correct them and hopefully gently explain what the difference is. But conjunctions are fun to look at. They're transient. You can watch the two bodies get closer together and then further apart as the days go through. Here's a conjunction of the moon and Jupiter. I took from my driveway in 2012, and you know it's Jupiter because if you blow it up, you can see 3 of the moons. Here's one of Venus, Mars, and a crescent moon showing some earth shine. This is light that's bounced off the earth and is lighting up the backside of the moon. If you were on the moon and looked at the earth, it would look the other way. The earth would be in a gibbous phase. And I'm kind of proud of this one because it was 12 degrees Fahrenheit when I took this. And you can't work the scope in a camera with gloves on. So this was a challenge, but it came out pretty good. Back in December, we had a very close conjunction of Saturn and Jupiter. This is 1/5 the diameter of the full moon. This was the closest conjunction of these two planets since I think 1623. And Steve Bolevia, one of our club members, made this beautiful shot showing detail on the surface of Jupiter and the rings of Saturn. This was a conjunction of Venus and Jupiter from they were just 1/4 of a degree, half the size of the full moon. That happened in the wee hours in 2014, August 2014. And again, taking with the telescope this time rather than just a long lens, you can see the moons of Jupiter. Venus tends to get overexposed and gets a little bit of a chromatic aberration in the lenses because it's so bright. And then this photograph I managed, and this was a planned photograph. I was going to Berlin for vacation, but I knew there was a conjunction, and I actually used Google Earth and a planetarium program to figure out where it would be and what the angles were. And I got the height of the Brandenburg Gate off of Wikipedia, and then conveniently was staying at the Adlon Hotel, which is right behind us. So I just went out and the weather was good, and I got this rather nice photograph of Venus and the moon. Unfortunately, they blocked off the street here because this was the beginning of the World Cup in 2018, and they have this gigantic TV that they put out so people on the other side the next day could come in and watch the soccer game. They had 25,000 people, and Germany lost the game, and so I'm glad I wasn't around there that night. Comets used to be thought of as being in the atmosphere. Aristotle thought that, and if you look at them, it kind of looks like they're something burning up in the atmosphere, but of course we know now that they're not. They were always thought to be bad omens up until more was known about them in the 17th century. And if you've ever seen the Bayeux Tapestry, which commemorates the Battle of Hastings, here it is. The men see the star, and here's the comet, and this happens to be Halley's Comet. Only in 1577 did Tycho Brahe prove that the comets were farther away than the moon. And Halley himself predicted the return of the comet of 1682, and it did return on time, and that really started off our true knowledge of what comets were. Comets are not moving in the direction that the tail is behind them. The tail always points away from the sun. Here's the orbit of this comet. There's an ion tail directly opposite the sun, and then the dust trails a little bit, but always in the direction away from the sun. We've had some fairly nice comets. They're not all that frequent. And one of the problems, of course, is the sky isn't as dark as it used to be. It seems back in the old days, there were comets practically every year, but we don't see those that often. The bright ones like Hale-Bopp and beautiful comet McNaught were really entertaining. This was more of a southern hemisphere object, but Hale-Bopp we all saw in the sky for a couple of weeks, and it was extremely bright. Most comets, however, are just little fuzzy blobs, and they move slowly in the sky. But over time, where if you looked at them with a telescope, you can actually see them pass through the star fields. And this video was made by one of our members in Yonkers. Many of you probably saw Comet Neowise back in July. It was a morning object at the beginning of July, and I went out in Larchmont Harbor and got this photograph. Because of the light pollution, it's not, again, as bright. I have friends that were out west that really got a great view around the same time. But then it passed into the evening sky, and here it is below the Big Dipper. And Steve Belavia made a close-up with a long lens telescope, and you can see the ion trail and the dust trail. We've visited comets. The first comet that was actually visited was Halley's Comet. A couple of probes passed through its tail, but we're getting closer and closer and closer. And then finally, in 2014, the European Space Agency sent the Rosetta mission up, and it followed comet 67P Churyumov-Gerasimenko. And yes, you have to practice saying that a few times before you can get it like that. And it actually landed a lander on the comet. They were hoping to have it be there for a while, but the comet's gravity is so low that the probe didn't, the Philae probe didn't really latch on properly. So it did manage to be there, but it was blocked from the sun, and it ran out of gas. So it only transmitted for a few days. But they got some valuable information about comets, and they took a lot of beautiful photographs, and you can see how detailed these photographs are compared to, say, something 15 years earlier. We're going to go out to the planets now, and the first ones we're going to talk about are the two inner planets, Mercury and Venus. They're never far from the sun, so you always have to look fairly close to the sun, either in the evening sky or the morning sky. Mercury only gets about 28 degrees away from the sun, and Venus only about 47 degrees. They're not much to look at in a telescope, although both of them can show phases. Venus, because it's much closer, the phases are much easier to see. You also have to be somewhat careful when it's beginning to get close to the sun, especially if you're looking in the daytime, as I'll show you. The best view of Mercury from Earth is this photograph taken at the Mount Wilson Observatory with the 60-inch telescope, which is the smaller of the two big instruments at Mount Wilson, which is a great place to visit, by the way. It's up in the hills above Pasadena, and it's free to visit it. You get a great tour. You can also rent this telescope to look at night. This is the Mercury Messenger view from a satellite probe that we sent up in 2011. You can see some of the features were actually properly detected in this difficult to obtain image. This is an image just last month that Steve Belavia took with a filter showing the sodium streaming off of Mercury because of the solar wind. Mercury is bombarded by particles from the sun, and it doesn't have an atmosphere. It has what's called an exosphere, and these are just charged particles and ions and nuclei and maybe some simple molecules that get pushed off the surface. And you can see this tail, very faint, but it's definitely there. And if you know what you're doing, you can make a photograph of this. Obviously, you can't see it visually, but the cameras are more sensitive. Venus is covered by clouds, and so it doesn't have a lot of features, although one of our members managed to use ultraviolet filters, and taking a picture of Venus in ultraviolet light showed some variations in the cloud strata. These clouds are made of sulfuric acid, so they're not fun to be around. We can peer through the clouds with radar, and the Magellan radar image has been put together, and it shows a very active surface on Venus. This probably was up until recently, and maybe even still, some volcanic activity on Venus. But Venus is not a nice place to visit. The surface temperature is extremely high, and the atmospheric pressure is extremely high, and so it's hard to imagine that there could be life there. There recently was a suggestion that there was life in the atmosphere because of the detection of phosgene, but the latest data I've seen on that suggests that that's not a real finding. It's based on some very, very subtle spectroscopic findings that are hard to really prove. But Venus has phases. Galileo was the first one to see the phases of Venus in September 1610, and that really locked the Copernican view of the solar system, that Venus was circulating around the sun. You can see it in the daytime. These are two daytime photographs. You have to build a big sun shield to make sure that you're not anywhere near the sun, or none of the sunlight falls on your oculars or your objectives. And you can see that as Venus gets closer to its inferior conjunction, that is between the Earth and the Sun, it tends to get larger because it's getting closer to the Earth, but it also tends to have a more crescent phase. As I mentioned, it's hot, it's dense, it's mostly carbon dioxide, but the Russians did land several probes on Venus. The longest one was Venera 10, I think, lasted for 2 hours. But this is the first image from Venus. But you can imagine these rocks are 864 degrees Fahrenheit in temperature, and the pressure on them is equivalent to being 3,000 feet below sea level in the ocean. Because these are internal inferior planets, they will pass between us and the sun on occasion. The transit of Mercury's happen about 13 times a century, and Mercury will pass in front of the sun. It's a dot, and we get very excited about it. But more exciting was the transit of Venus, because these only happen about every 100 years. And there was one in 2004, and there was one 2012. And for the 2000, I saw just a little bit of the end of the 2004 one. And I really wanted to make sure I saw the 2012 one. So we went to Hawaii and saw it from the top of Mauna Kea. And that was pretty incredible. It takes about 5 hours or 6 hours to run across the sun when it's in this position. And there's no fireworks or anything, but again, it's an amazing event to see. And of course, the next one is a little bit away in the distance, and banning some medical miracles. I don't think we're going to be seeing it. Going out further to Mars, Mars, of course, is in the news practically every day. There's our rover is running around on it. The Chinese now have a rover. There are satellites from United Arab Emirates and India and some other countries that are European Space Agency that are taking readings. We've mapped it down to a very, very fine resolution, something like 6 inches. We have some very sophisticated instruments that are scanning it both from the sky and especially on the ground. Mars made a close approach in last October, and it does that just about every 26 months or so. And the reason is, as you can see from this animation, that the rhythm of the orbit of the Earth and the orbit of Mars are such that they'll get to a close approach in opposition, and then they get out of sync. And so the next time they're in the right position, it won't be for 2 more years. Here was the size of Mars, the distance from the Earth, about 0.41 astronomical units. That is 0.41 times the distance from the Earth to the Sun. And then it'll be very far away and get very small, and then get big again in just December 2023. It was about 22 arc seconds in diameter in October. The biggest it ever can get is about 25. That was how big it was back in 2003. But even when it's down in this area next in late 2022, you'll be able to see some of the surface markings. This is kind of what it would look like in a telescope. With cameras, you can do a little computer processing and get some better images and more detail. A lot of club members took photographs this past October. These are just a few, and John Palladini and I were exchanging images, and we both realized we actually had managed to capture Olympus Mons, the big stratovolcano that is the biggest volcano in the solar system. And you can see just a little white spot here, and John has a little bit bigger telescope, has maybe a little more definition. But you can see how much detail you can get. It's very hard to see this detail unless you have a very large telescope. because of the atmosphere, which we'll talk about in a little bit. But you can also understand how Percival Lowell, doing visual observing back around 1900 out in Flagstaff, Arizona, thought he saw canals, because you can see these linear streaks and features. And when you only get to glimpse them for an instant, your mind puts together what these might be. And so he drew maps and was convinced that these were canals built by the engineers on Mars to pull water from the polar caps down into the barren areas. Mars is pretty barren. Here's a photograph from Perseverance, just taken in April. Some of you may have watched the landing. It was really incredibly exciting. This rover has a lot of very sophisticated chemical analytic equipment, and hopefully we'll find out more about some of the chemical constituents of these rocks and perhaps evidence of organic material. But we do have an incredible satellite that's flying around Mars, the Mars Reconnaissance Orbiter, and it has a camera on it called Mars HiRISE. It's operated by Arizona State University. And you can go on their website and see incredible photographs of Mars with amazing detail. And many of them are also shown as 3D images. So if you have those anaglyph glasses, the red-blue glasses, you put them on and you can just see yourself, you're essentially on Mars. It's really kind of amazing. The photographs are really remarkable. Here's Olympus Mons. You can take pictures of the rovers. Here's Curiosity. And here's Perseverance as it was landing, still attached to its parachute on February 18th. So it's a really great site to take a look at, and there are probably 30 or 40,000 images that it's taken up to now, and continues to produce these incredible, amazing images. Going out further, the asteroid belt has a large number of small particles and a small number of large bodies. The largest is Ceres. Just a few days ago, Steve took a picture of Vesta, the fourth one to be discovered and the second largest. That shows how it moves just in 80 minutes. So if you look at these through a telescope, they still look a little bit like stars in the sense that you don't really perceive a surface, but you can see them move fairly obviously against a starry background. And this is just with a 2.8-inch telescope. But we've sent space probes up. The Dawn spacecraft went to Vesta in 2011, and then it went to Ceres in 2015. And it made these images that have been animated. Ceres is a dwarf planet. It's not officially an asteroid because it's round, and it is probably made of some water ice with rock, and maybe has a subsurface ocean, and some of that stuff is kind of percolating through, and you get these salt deposits on the surface. Vesta is cratered, and it has a kind of a large crater at the top, and there are some meteorites on Earth that are believed to be part of Vesta. And then just in October, the Osiris-Rex probe actually grabbed a piece right there. And it's estimated that it has between 400 grams and a kilogram of material that will be returned to Earth on September 24th, 2023. And if that goes well, then they'll be able to analyze some truly primitive material from the earliest part of the solar system. At current count, there are 1,083,453 asteroids that actually have numbers. And of course, there are probably hundreds of millions that are so tiny that we'll never really label them or be able to track them. Going out further, Jupiter, um, many of you have seen it in a telescope. This is a view of Jupiter, what it might look like in an 8-inch telescope on a good night. Jupiter and Saturn are both truly remarkable objects to see. Unfortunately, this year they're fairly low in the sky. They'll be visible towards the end of the summer, but they're low in the ecliptic, so there'll be a lot of atmosphere between us and them. So the views might not be as good as they will be in a couple of more years when they rise up higher into the sky. Jupiter is beautiful and has all these storms that continue to gyrate around the planet. The Great Red Spot has been there since it was discovered in the 1600s. It sometimes gets bigger, sometimes gets smaller. It's been a little less red lately than it's been in the past. Nobody's really quite sure why. It just doesn't disperse like all the other storms. What's interesting about the bands, though, is that the movement of the winds on Jupiter isn't all in the same direction. As you can see here, it's a loop about 3 seconds long, but you can see that above the red spot, which is anticyclonic, it's like a hurricane on Earth. It goes in a counterclockwise direction, but the overall movement of that band is from east to west, and then above it there's a band moving from west to east. There are a lot of cyclonic storms at the poles. We now have a spacecraft, Juno, that is in a polar orbit around Jupiter and has been taking measurements and making pictures of these incredible storms on the planet's poles. Galileo discovered the 4 moons of Jupiter in January 1610, and he made drawings. All of them were thought to be like Earth's moon until we sent Voyager up there in 1980. I think it passed Jupiter, and it sent back these pictures showing that these 4 Galilean moons are completely unique and different than each other. There are currently 79 moons total, but most of them are tiny. But these 4 are very easy to see. You can't really see the surfaces, but some larger telescopes can see that the colors are a little bit different. Io, which is the closest, is a volcanic body. It's heated. Its interior is heated by tidal forces because it's so close to immense Jupiter. And Europa is covered by ice and probably has a subsurface ocean. Ganymede looks a little bit like it's been taken apart and put back together again. And Callisto is heavily cratered. These moons pass in front of Jupiter, just like our moon sometimes passes in front of the sun, and in front of the Earth, rather, and blocks out the sun. And you can see shadow transit, this one of Io, and sometimes you can see double shadow transits. So here's a transit of Io and Ganymede. Ganymede was off out here, just a little bit out of the picture, and Io was actually right in there. I think it's right in here. But usually you lose the planet when it crosses, with the moon when it crosses over the disk of Jupiter. But these are nice to watch because they take about an hour and a half. And you can actually see the progress of the eclipse as it crosses the face of the planet. Europa is made up of these ice flows, and there was a lot of debate as to how thick these were, how thick the ice was. It's now thought it's about at least 10 kilometers. But it's clear that this is not a surface that has been impacted by meteors or any other bodies. It's just basically like a lake that's been broken up and continues to move. The Hubble Space Telescope detected a signal of water by ultraviolet. You have to believe the data here, but it's pretty well established that there's some water shooting out of cracks in Europa's surface. The volcanoes on Io are easy to see, and the Voyager probe saw some of them, and then some of the other Galileo probe made this photograph. And I think there are 125 active volcanoes on Io, and they spill a lot of sulfur compounds, and that's why it's all yellow. Saturn's rings are everybody's favorite. When you show them to someone who hasn't seen them, the first thing they say is, "It's not real." You know, you drew it on the front of the telescope. Um, uh, but they are real. What's remarkable about them is they're basically made of water ice, and the average thickness is only 30 feet. So there's Saturn 800 million miles away, and the rings are so reflective that we can see them even though they're 30 feet thick. Because of the tilt of Saturn in its orbit, the rings open and close over a period of time, and they're beginning to close up now. They reached their maximum in 2017, and they're starting to close now, and I think 2023 or 5, there'll be about a 3-month period when Saturn won't have a visible ring, because it'll be exactly at the same plane as the Earth. Saturn's moons are not that difficult to see with an 8-inch or larger telescope, at least the brighter 3 or 4. And here's a photograph. It's actually a double photograph. He took a picture of Saturn and then he overexposed it to show the moons. The difference in magnitude between the moons and the surface of the planet makes it difficult sometimes to make one single photograph. The Cassini spacecraft circled Saturn for about 10 years. Excuse me, it was 13 around Saturn. It took 453,000 images, as well as making innumerable numbers of magnetic and other kinds of measurements. Made 294 orbits until it was crashed into the planet so it would burn up. And if there were any Earth microbes on it, it wouldn't contaminate the system. And it found some amazing things. It found spokes in the rings due to gravitational interactions and collisions between the bodies. It found these little moons. Here's a moon with casting a shadow, so-called shepherd moons. And it found that at the poles there were these hexagons. You would think that everything in a rapidly spinning gaseous body, everything would be concentric circular. But in fact, at the top of Saturn is a hexagon. There are some theories about how the fluid dynamics work to create this rather than making it a circular feature. It's a little circular at the top, but not here. But the dynamics are not yet fully proven. Saturn has 82 moons, of which about 8 can reasonably be seen with a large telescope, and certainly 3 or 4 of them are easy with a smaller telescope. And they're all different. Iapetus is dark on one side and light on the other. Mimas has this gigantic crater. Enceladus, again, like Europa, is made of ice and has a subsurface ocean. And Tethys also has a gigantic hole taken out of it. And Titan has an atmosphere and a very interesting chemical makeup, and probably has a rain cycle, although it rains methane and not water. Enceladus ice is probably thinner than on Europa, and so some of the water is escaping. There's a plan to send a probe to pass through and collect some of this material. Cassini did fly through and detected some hydrogen, but it wasn't able to collect chemical samples. So if we can get some of this chemical stuff, we might find organic chemicals, or maybe even a little Enceladus organism that got pushed out and was living in that subsurface ocean. But it's going to be a while. Titan has a surface. It has lakes of liquid hydrocarbons. Its atmosphere is nitrogen, but the surface is probably made of frozen water. And it looks like it has rocks, but this is probably frozen H2O. And there is a theory that there may also be a subsurface ocean of water underneath this surface of frozen water and lakes of hydrocarbon. It probably smells pretty bad on Titan because of those hydrocarbons. Uranus and Neptune are the so-called ice giants. They have rocky cores surrounded by ice and hydrogen and helium. They can be seen as actual disks in a telescope. If you have about 4-inch scope or a little bit larger, you'll be able to see that. There are 27 moons of Uranus and 14 of Neptune. Both of these planets have very, very thin rings that are very, very difficult to see, but they can be detected as a star passes behind the planet, and the rings decrease the intensity of the starlight by just a small fraction, but that can still be detected. Pluto, it says the planet Pluto. We now know that it's not a planet, but of course, maybe it is a planet. Who are we to say? Pluto knows whether it's a planet or not. Here's the Discovery photograph, and you can see that Tombaugh, when he did this, he stayed up all night to guide the telescope. Then he developed the plates. Then he stared at them through something called a blink comparator, and flashing one plate versus the other plate to see if any of these things moved. And he was able to see that this little body here was not present here, and it was present here when it wasn't present there. So this is the Discovery image of Pluto. But of course, we've sent New Horizons that arrived on July 4th, 2015, and really one of the greatest things that's happened in the space age. A journey of 4 billion miles, and they got it within 60 miles of the place where they thought it would be when it went by at 33,000 miles an hour. And it made these incredibly detailed photographs, made a lot of scientific measurements. Pluto and Charon are actually a dual planet system because they circulate around a common barycenter, a center of mass that's actually outside of Pluto. The Earth-Moon system, for example, also circulates around a common barycenter, but it's within the body of the Earth. So even though the Earth is tugged on by the Moon, it doesn't appreciably move if somebody were to make the same kind of photograph. But you can see Pluto circulating around an axis around here. New Horizons went on to another body that was only discovered in 2014, named Arrokoth, and it made this picture. This is obviously not something that you can see with an Earth-based telescope. This was originally discovered by the Hubble. This body is only 36 kilometers in length, and it's 6.6 billion kilometers away. It takes 6 hours for light to get, or radio signals to get from Arrokoth to Earth. But one of the theories is that many of the bodies in this part of the solar system, the so-called Kuiper Belt, might be these kind of combined double planets that have joined. They've stuck together and have fused. Here's a picture of Makemake, which is another Kuiper Belt object that Steve took, and you can see. And now, of course, we have computers that do what Clyde Tombaugh had to do, and actually you don't even need to make a photograph and stare at it. The computers will actually do all the work for you and detect these objects. So many, many Kuiper Belt objects have been discovered and plotted, and now you know that there is a whole vast number of objects beyond the orbit of Pluto, or concentric with the orbit of Pluto, at the distant parts of the solar system. Makemake actually itself has a moon that was detected by Hubble. So here's a plot of the solar system in a logarithmic fashion, so factor of 10 going out each way. And the Kuiper Belt is this area of small bodies, distant, of which Pluto is a member, and it is just at the same area, or just a little bit interior to the heliopause, which is the limit of the sun's electromagnetic influence. Voyager 1 and 2, as of Sunday, are at these distances, heading out into interstellar space. Going much further, there is a theoretical zone called the Oort cloud, which contains trillions of cometary-like bodies that are just balanced between the gravitational pull of the sun and the gravitational pull of the nearer stars. We think that some of the long period comets or the comets that crash into the sun come from the Oort cloud. Eventually they get pulled in either because another passing star goes by, it perturbs the orbit, or there's collisions, and then they end up coming towards the sun. And you may know that there were two objects in the last few years that passed by the sun that probably both came from beyond the solar system on the basis of their orbits and their speeds, and that was Oumuamua and what was called Comet Borisov. Oumuamua didn't look like a comet, and there's a professor at Harvard, chair of the department, who thinks that it might be a light sail from a distant civilization. That's a minority view, and the real problem is we'll never actually know because it's going out of the solar system now. So what's beyond? What beyond is our galaxy, the Milky Way. And many of you have been in dark areas where you can see this beautiful swath of stars and dust, best seen in the summer and winter, and made up of innumerable stars, as Galileo noticed when he first turned his telescope on it in the fall of 1609. We live in an area of the Milky Way that's about halfway or a third of the way between the center of the Milky Way, which contains a 4 million solar mass black hole, and its most distant parts. We look in that direction in the summertime, and we look in the opposite direction out towards Orion in the wintertime. It's thought that our Milky Way probably looks a lot like this galaxy, NGC 6744. It has about 400 billion stars and 2.5 billion solar masses of gas that's still in there. It's probably about 100,000 light years across, but it's only 1,000 light years thick. And the Earth, or the sun actually, with the Earth going around it, circulates around the Milky Way about every 250 million years. And when the Earth does that, when the sun does that, it goes up and down. It passes above and below the plane of the Milky Way in kind of a sinusoidal way. Yeah, here's a combined photograph, not a terribly good one because I had some artifact, but this is looking south from an area up in the Colorado mountains, and you can see some of the star clusters, M6 and M7 and M8, M20, the Sagittarius star cloud. Sagittarius is in here, and right about at this point, if we were to go 25,000 light years, we might get to Sagittarius A star, which is the black hole at the center of the Milky Way. And you might say, how do we know that? Well, the answer is that people have been taking pictures of that area. It's obscured by dust in the visible wavelengths, but infrared can actually pierce through that dust and follow the path of the stars. And you can see this star, which is S2, circulates around something, and it's moving faster at the lower end and slower at the upper end, which is typically the way a star moves in an elliptical orbit. And this has been plotted out over the last 25 years by the UCLA Galactic Center group, mostly using the Keck telescope in Mauna Kea. And they, for that work, Andrea Ghez won the Nobel Prize last year. And here is the plot of the closest stars to Sagittarius A star, which would be right here, right at the bottom of this orbit. A few years ago, some gas passed by, and some of it fell into the black hole. Here's a picture of the star going around, and it made its closest approach about 120 astronomical units from this putative black hole. Here's a infrared view of the gas falling into Sagittarius A star. Stars come in a bunch of different sizes and and temperatures. They all have the same shape. They're round. And a lot of information was gained from the work of the Harvard computers, these women who examined thousands and thousands of plates with little spectra on them that were made on a bequest by the widow uh, of, uh, of Henry Draper, of Draper Park in Hastings. And he was a professor of medicine at NYU, and his father actually founded NYU Medical School. And when he passed away at a young age, his wife gave a bequest to Harvard. And Henry Draper was the first person to make a photograph of a spectrum of a star. These women examined plates diligently for many, many years, and they figured out the relationship between the spectral characteristics of stars and their temperatures and eventually their sizes. And this is all covered in a really great book, The Glass Universe by David Sobel. Our sun is a Class G star. It's relatively small relative to the larger stars, although most of the stars in the galaxy are M and K stars. The larger a star is, the hotter it is, but also the shorter its life is. So these very large, hot, young O stars will maybe last for 10 or 20 million years, whereas the sun is already 4.5 billion years old and will last another 4.5 billion years. And some of these M stars might last for trillions of years. The temperature of a star is correlated with its color. So the hotter stars are blue or white, then they're yellow, and then they're red. And the red stars are the coolest. And so when you look at some double stars, you can see the differences between the colors rather dramatically. So in Gamma Andromeda, for example, the blue star is hotter than the yellow star. Same thing for Alpha Hercules, which is a good star to look at this summer. And Beta Cygni, or Alberio, is a showpiece of the summer sky because they're both very bright. You can see the hotter blue star and the cooler yellow star. Stars are all born in a star-forming nebula of gas, probably compressed by supernova explosions from stars from a generation earlier. They form a protostar. This is an actual photograph of H.L. Tauri from the ALMA telescope in Chile. If the star is a normal-sized star or a small star, it'll form a star that will live its life. Eventually, it'll use up its fuel and become a red giant. And when that happens, it throws off its outer shell, and it becomes a planetary nebula, which at the center has a white dwarf, which is a star that is very hot, but doesn't have any nuclear reactions anymore. It stays together against gravity simply by its electrostatic structure, its molecular structure. If the star is large, it forms a main sequence star that has a high mass, burns up its fuel very quickly, eventually becomes a red supergiant, converts helium to carbon and oxygen, and then maybe even to, I gotta go previous, whoops. That's what happens when you squeeze the mouse too hard. It becomes a red supergiant, and that will end up not being able to resist the force of gravity. It becomes a supernova and has one of two fates, either a black hole or a neutron star. So when we look out at the night sky, we see the constellations that the ancients put together, but what most of us like to look at as amateur astronomers with telescopes are what's called deep sky objects, the different types of things that are in the sky besides stars, clusters of stars, galaxies, and nebulas. And these are deep space objects. They run the gamut from things that are not that far away from us to things that are very far away. We call them faint fuzzies because they're faint, and we have to work hard to try to figure out exactly what their shape and size is. We don't see them in color, even though we're very used now to seeing color photographs of these objects. And sometimes you have to use what's called averted vision. You can't look directly at them because the part of your retina that's directly opposite your lens is not the most sensitive part of your retina. So you look off to the side and you actually end up seeing more. But we're now used to having good cameras and sensitive chips and doing computer processing and exposing for a long time. So we get color and detail from what otherwise might be just a smudge of kind of grayish green material. It's still fun to look at this stuff, and it's great to get those actual photons into your eyes. But we are able now to explore the night sky with much more detail. Well, why are we limited in what we can see? Well, there's a number of reasons. The first is the fact that our eyes aren't very sensitive. We evolved to look during the daytime, and this is the spectral curve, spectral sensitivity of the human eye. But stars put out their electromagnetic energy in a much broader frequency range, so we don't get to see the stuff that's on either side. The cameras are much better at it, and that's why they can show us much more and show it to us in color. But we are rather limited. In addition, our rods are the most sensitive, but they need time to increase their concentration of rhodopsin, and we only maximally dark adapt after 20 or 30 minutes. And it only takes one flash of white light to completely bleach the rods of their rhodopsin, and then we got to start over again until we get dark adaptation. And it's one of the reasons why we ask that everybody use only red flashlights when they're on the observing field, because you can lose this dark adaptation extremely quickly. We get older and we have floaters in our vitreous, and we have small calcium deposits in our lenses, and the shapes of our eyes changes, and we get some astigmatism. That really, we can do something about the cataracts. You can't do much about the floaters. And it's one of those things, you just have to live with it. It's a good reason to start your kids in astronomy early so they get the best view when they're young. Just as you should have them start listening to good music young, because when they get older, they won't hear it as well. Light pollution is a terrible problem. Light pollution is growing twice as fast as the population. We're stuck here in this area, which is just blazing white, as is most of Western Europe. If you really want to see a dark sky, you got to go out west or maybe up to Maine. Down to Chile is a very good place to go. And what the light pollution does is it just washes out the contrast in the sky, because the frequencies of light are going up and scattering in the atmosphere. And even light that is directed downwards, some of it will reflect up and still scatter. In addition, a lot of the lights now, the LEDs, are enriched in the blue wavelengths, and the blue wavelengths scatter more than the red wavelengths. So it just increases the amount of contrast loss. We got weather, and we got a lot of weather around here. And this is just from a couple of days ago, and you can see a massive amount of clouds over our area. Not much we can do about that except to hope and maybe make some travel plans to take a small telescope out to the southwest. And then there's the atmosphere. We have to look through the atmosphere. The Hubble Space Telescope doesn't, but every other telescope does. And the atmosphere has a lot of heat currents in it. It doesn't have a constant temperature from top to bottom. And light, as it goes through air of different temperatures, the refractive index of that air is different, and so everything shakes around. And this is an actual video that I made in October of Mars. When you look with your eyes, every once in a while it'll settle for a fraction of an instant, and you'll get a lot of detail, and you just have to be patient. Fortunately, the computers can take these video images and do some processing and bring out some of the detail that you saw earlier in the Mars photographs that I showed. We have small apertures. I'm very happy to look through a 4-inch telescope here. Unfortunately, you can't put an eyepiece on the MMT at the Whipple Observatory. It's just going to have a camera. You can rent the 100-inch at Mount Wilson. That's the largest scope that I think you can rent in the world. And you can put an eyepiece on that. But most of us have to be satisfied with scopes. The club owns a 20-inch telescope. I know some people that own a 30-inch telescope, but beyond that, it's pretty tough to get more aperture. And of course, the bigger it is, the less portable it is. And then, of course, there's time. We don't. our eyes don't work the way a bulb exposure works on a camera. And we just maintain the images for just a short period of time before we renew them. And that's something that a camera can do. It allows us to make those photographs. Here's the menu of deep sky objects: open star clusters, planetary nebulas, supernova remnants, emission nebulas, globular star clusters, and galaxies. And we'll go over each of these in just a little bit of detail before we finish. Open clusters are groups of stars that have been born together. They're scattered all over the sky, but mostly we see them relatively close to the Milky Way. They form from a common envelope of cool gas, and then when gravity contracts them, the stars will form. A lot of them have interesting names. People have been observing them for a long time, and we can follow the evolution of these stars by looking at their colors and their temperatures and their spectra, because they may all form together, but they don't all form at the same size. And in fact, here is M35 and a more distant open cluster, NGC 2158, make a very nice pair. So these are fun to look at. The most famous of the open clusters is the Pleiades, known since antiquity, mentioned in the Iliad and even in the Bible. And the Pleiades really are over 1,000 stars in the cluster, but we see mainly 7 of them. That's why they're called the Seven Sisters. Every culture on Earth has interesting stories about the origin of the Pleiades. These were the daughters of Atlas, and they were being chased by Orion in our culture, but they were Indian maidens chased by bears in the Kiowa culture, and they were placed on top of Devil's Tower, and the bears clawed up the side of Devil's Tower, and that's why Devil's Tower has those gorges, those gouges in it. And then the Great Spirit put them up into heaven so that the bears couldn't get to them. The dust that you see was only discovered in 1859, and it's actually not the material that these stars were made from. They're just passing through this dusty area because this cluster is old enough that all the gas has been used up. But there are some clusters that still are associated with the gas that they were born in. As the molecular cloud compresses, the stars are formed. The radiation from the stars heats up the hydrogen that's outside the cluster, and we see some of that, and then the cluster stars evolve. The trapezium in M42 is an interesting area, and I'll show you a bigger photograph in a minute, but you can see all the dust and hydrogen being heated up by these very, very hot, very young stars that are just a few million years old. Similarly, the Lagoon Nebula in Sagittarius, which would be very visible this summer. Same thing, small cluster, and then heated dust and hydrogen. And here are some other ones: the North American Nebula in Cygnus, and also a summer object. The Bubble Nebula, which is actually a bubble of hydrogen gas heated by a particular kind of hot star that has a very, very active solar wind and is putting out a lot of particles that blow it up into an actual bubble. The Heart Nebula, it looks like a heart. And here's the cluster and another cluster. And then the Swan Nebula, also a beautiful summer object, an easy one to see in a small telescope. In Orion, the Flame Nebula, which has not only hydrogen gas but some dust, is heated by Alnitak. And the Horsehead Nebula, which is another tongue of dust sticking into this collection of gas, is actually heated by Sigma Orionis, the star over here, also a hot O star. And here's the Orion Nebula with the trapezium in the middle. This is an area of active star formation, and the Hubble telescope has detected a large number of new planetary systems that are being born in this nebula. And here's one of them, high magnification. You can see the torus of dust that is beginning to form planets, and the star, just newly born star right in the middle of it. Globular star clusters are larger numbers of stars, sometimes in the hundreds of thousands, and these are much older than open clusters. It's thought that they probably formed in the same way, but the conditions in the universe 12 billion years ago, when these were formed, were quite different. And so these are almost all older stars with low metal content, and they are outside the Milky Way, surrounding it in kind of a sphere. And there are some very beautiful ones. Omega Centauri is so big that it's actually thought that it might be the core of a galaxy that interacted with the Milky Way. This is a southern hemisphere object, as is 47 Tucanae, which is in the Small Magellanic Cloud. But these two are northern objects. You can see them this summer. Messier 13 is the great cluster in Hercules, and M92, also in Hercules, is its little brother. And these are collections of several 100,000 stars. But they exist not in the planet of the Milky Way, but actually surrounding it. And every galaxy appears to have some globular clusters. There's about 150 associated with the Milky Way that we know about 500 associated with the Andromeda galaxy, and about 13,000 of them associated with the gigantic M87 elliptical galaxy that's in Virgo. We mentioned before planetary nebulas. These are exploded stars with a white dwarf at the center. You can actually see the white dwarfs in some of these planetary nebulas. You can see it here, and probably here in the Dumbbell. This is a fairly easy one to see in the summer. It's in the summer triangle, and it's very easy to see. The Owl is a little bit fainter. It's up in the Big Dipper. There are many planetary nebulas. These were named by William Herschel around 1787 because in his small telescopes, they looked a little bit like Uranus that he had discovered in 1783. They're just little bluish round dots, but we now know that they have a lot of very incredible internal structure that the Hubble has found. Supernova remnants. There's not too many of them in the sky. The two most famous ones are the Veil Nebula, and this is a very large area. This is about 36 times the surface of the full moon. And then the much smaller Crab Nebula. The Veil Nebula probably was from a supernova explosion about 20,000 years ago. But the Crab Nebula the explosion was observed by the Chinese in 1054 AD. And it has as its center this particular star, which is a neutron star. That is the star that actually created the supernova. And we know that because we can actually see it pulsating in a very slowed down manner here. And this is an X-ray photograph showing the shock waves from this neutron star that is rotating. It's a pulsar with a rotation period of 33.30285883 milliseconds. The timing is down to the billionth of a second. And what's happening is that the star is spinning so rapidly that it is sending out charged particles in its rotational axis, and because of its angle, that beam is crossing the Earth every 33 milliseconds, and so that's what a pulsar does. And if you could, this is a photograph that one of our members took, and you can actually see the star right there. So if he could get a shutter working and have a sensitive enough camera, he could make this photograph. We do see supernovas in other galaxies. The last supernova to be seen by the naked eye from Earth was in 1987 down in the southern hemisphere in the Large Magellanic Cloud. The last one in our galaxy was in 1604. That was observed by Johannes Kepler. It would be pretty cool to have one because you can see them in the daytime if they're close enough, but you don't want them too close because the amount of radiation and energy is pretty intense. But here's one in the M51 galaxy, kind of a rough video photograph, but there's supernova 2011 DH. With the new survey telescopes that are coming out, like the Rubin telescope in Chile, they'll be finding thousands of these every week, maybe even every day. Galaxies, now we're going much further out. These galaxies are now millions of light years away. They come in several forms, either spiral galaxies or elliptical galaxies. There are some intermediate forms. Um, Edge-on spirals are rather beautiful. You can see the dust, and this would be the same dust that we saw from inside our Milky Way. And then you can see some that are more face-on, sometimes directly face-on, and then the elliptical gigantic galaxy M87. These are endlessly fascinating and great objects for our club photographers. And the ones that are brightest are probably in the millions of light years away. And then there are some that are further away, as we'll talk about in a second. Bode's Nebula, M81 and M82, are within half a degree of each other. And M82 is a star-forming galaxy. All the red here that you see is hydrogen gas that is heated up by new forming stars. So this is what's called a starburst galaxy. M51 is actually two galaxies that are interacting. The larger one is actually eating up the smaller one and throwing out stars gravitationally. And you can see this halo of stars that are being thrown out. And actually a deeper photograph of this will show this kind of all through the whole area. This is the closest large galaxy, the Andromeda Nebula, M31. It's a naked eye object. We see the core in the fall. It's very easy to see in a dark sky, and can be seen from Westchester, from up in Ward Pound, where we have our star parties. It has companion galaxies, M32 and M110. And many of these larger spirals have these kinds of companions. Andromeda is actually approaching us. Even though the universe is expanding, Andromeda and the Milky Way are gravitationally connected, and they're approaching each other at 68 miles a second. And it will arrive at our doorstep in about 4.5 billion years, at which point the two galaxies will merge. They'll kind of rotate around each other, throw off some stars, and eventually settle into becoming an old elliptical galaxy. This is a photograph I took in Chile showing the southern Milky Way and the large and small Magellanic Clouds. We can't see this from our area, but here are Alpha and Beta Centauri, the Southern Cross, the Coal Sack Dark Nebula, and Eta Carinae, which is a star that might go supernova soon, which soon in astronomical terms means something like either tomorrow or 100,000 years from now. But when we look out at these galaxies, if we pay attention, and our photographers can give us some nice deep images, we can see galaxies that are very far away. So here is an image from a 6-inch telescope by somebody, Steve, who really knows what he's doing. And we have a galaxy here that's 54 million light years away. But down here, we have a galaxy that's 343 million light years away. And over here, we have a galaxy that's 1.3 billion light years away. So when we go out in distance, we're going back in time. The light from this galaxy started 1.3 billion light years ago, when the Earth was only about 2/3 of its current age. If we look at even further, it's difficult to use earthbound telescopes, so we use the Hubble Space Telescope, and we can see galaxy clusters that are as far as 4 billion light years or even further away. These are so massive collections of galaxies that they bend the light of galaxies behind them, and you can see these streaks, these arcs. Here's a big one over here. And this is light from distant galaxies that have been passed through the curvature of space caused by the massive amounts of matter and dark matter in these galaxy clusters, as predicted by Einstein's general relativity. But we can go back even further. Hubble took this photograph, the Hubble Ultra Deep Field. And everything you see in this photograph is a galaxy. Every speck of light is a galaxy. There's nothing in this photograph that's in our Milky Way. And it contains, almost invisible on the photograph, but when blown up by the people that made it at NASA, the Space Telescope Science Institute, you can see this galaxy, which is thought to be the most distant galaxy yet imaged, so-called GNZ11. It's 13.44 billion light years away. So is there anything further than that? And the answer is yes, there is something further than that we can see. And even though you can't see this galaxy, you can see what is further away than this galaxy. When we look out, we look back in time. We don't use distance anymore. You can't say how far the center of the Milky Way is because it's quadrazillion miles and nobody knows what that means. So we just talk about light time. And we said that GNZ11 is 13.4 billion years ago. The light started 13.4 billion years ago. So what do we know about the universe? How did it start and how do we see it? After the Big Bang, we know the universe is expanding. So if you run the movie backwards, it had to contract and eventually it was a point, and that was the Big Bang. And after the Big Bang happened, the universe was very hot. 1 second later after the Big Bang, it had a temperature of over 100 billion degrees, 100 billion Kelvin. And all it did was consist of protons and electrons and neutrinos and photons, energy particles. And in this hot soup of particles, the photons bounced off the charged particles. They couldn't pass freely through the universe. So the universe was dark. It was a fog. But the universe was expanding. And eventually it expanded enough, and when it expands, it cools, which is exactly how your refrigerator works and your air conditioner. So the universe expanded and cooled, and eventually it cooled enough that these independent electrons and protons could get together and form neutral hydrogen atoms. And at that point, the photons were free to pass through the universe and move through the universe to eventually we could see them. But the universe was continuing to expand, and so continuing to cool. And when it did that, it stretched the wavelength of these photons out. And by the time they reached us, their temperature was such, they had a wavelength that suggested that they came from an object that was only 2.73 Kelvin. That is 2.73 degrees above absolute zero. We can detect that 2.7 degree wavelength. It's in the microwave. So we put together this device. We didn't put it together. Bell Labs did it. And it was used by Penzias and Wilson in 1964 to discover this hiss that was constantly throughout space in the microwave spectrum. This device, by the way, is in Homedale, New Jersey. You can visit it. It's a National Historic Landmark. It's right off exit 116 of the Garden State Parkway, only 27 miles from downtown Manhattan. But all it could say to us was there was this hiss of a frequency that reflected a 2.7 degree temperature of deep space. So in 1989, the Cosmic Microwave Background Explorer satellite was sent up, and it mapped the entire sky. We sent up one a few years later called WMAP, the Wilkinson Anisotropy, the Wilkinson Microwave Anisotropy Probe that refined the map. And then recently, the ESA sent up Planck, and that made a very fine map. There's also a telescope in the South Pole at 10,000 feet elevation that's looking at this. And they made this map. Now, this just looks like a big egg that maybe somebody buried at Easter, but in actual fact, it's the entire sky that's kind of been unwrapped. And it shows that this temperature that we're seeing, these photons that we're seeing from the early universe, differ with a temperature between the blue and the red of just a 10,000th of a degree. And this reflects quantum processes that occurred right after the Big Bang. But it also means that the density of the gas at the time, 380,000 years after the Big Bang, the density was slightly different. And these cooler areas went on to form stars and eventually galaxies. We don't see those first stars yet, although hopefully some of them will be seen if the James Webb Telescope goes up. This is a little bit of a hard way to see it, so let me show it to you in this picture. Here we are at the center in the Milky Way, And if we look out, we're looking back in time, and we'll see galaxies as they were 5 billion years in the past, and then some 10 billion years in the past. And eventually we'll look past the first galaxies and stars to the cosmic microwave background some 13.8 billion years in the past. We can't look any further than that, at least not in the electromagnetic spectrum, because the photons were just bouncing off the charged particles. So how do we look at those particles if we don't have a detector out in space? We can see them because the photons are still bouncing around now, even though they've been cooled to 2.7 degrees. And we can detect them. You go up in the attic, you get your old cathode ray tube television that you put up there 30 years ago when you got your first LED television, figuring, well, I might need it someday. And it's been sitting up there gathering dust. But if you take it out, turn it on, and tune it to channel 6, 1% of the dots that you will see are actually cosmic microwave background photons. They come from the beginning of the universe, as far back as we can see. To go back any further, we would have to detect relic neutrinos that also have been redshifted to a very low frequency. And there's no way to do that yet, although there is one possible experiment that's been suggested to do that. And we think we know about some of the conditions of the universe because of the concentrations of hydrogen and helium in deep space, the formation of which depended on certain theoretical calculations about the temperature and composition of the early universe. But this is the farthest thing that we can see. And even though you can't see GNZ11, you can see cosmic microwave background photons. Beyond that, we just don't know, and we still have a lot of questions. But even looking at simple things in the sky begins to connect us to some of the deeper questions about how the universe was created. So I'll end with that, and if there are questions or comments or anything else you want me to explain, I'm happy to do so. I'll stop the share. Paul?
All right, very good. Thank you, Larry. Thank you, everybody. I'm sure if you have any questions, let's go right ahead and you can unmute yourself. You can temporarily just hit your space bar and speak, or go ahead and unmute yourself. I want to say hello to everybody. I see a bunch of club members here and people that are guests or people that are just joining us for the first time. Again, I want to say welcome, and I hope you enjoyed it, and thank you very much to Larry for just a stellar presentation.
And I want to thank some of the astrophotographers in the club. I see Steve is on. Steve sends some of the most amazing stuff that you could possibly imagine, and he doesn't use big telescopes for it, right, Steve? I think your biggest scope is 6 inches, right?
I don't even have the 6-inch anymore. It's my largest scope, I think now. Well, no, it's true. I have my Celestron C6. All right, so but I use that that's just for planets now.
Yeah.
So, yeah, the galaxies are fine in small telescopes. Yeah. Thanks.
So,
awesome.
Yeah, the photographs were fantastic from all of our members. Just unbelievable. I mean, Astronomy Magazine, good.
Yeah, well, I think that we were talking about that. We were up there a couple of weeks ago. We had a kind of a star party in the clouds. It wasn't much of a night, although one new guy had a new CPC 800, and we showed him how to use it, and he was pretty happy. But we were talking about the level of sophistication that just in the last couple of years that people have graduated to. Their equipment is better and working better. They've learned how to do guiding. They've learned how to do processing. Some of the instruments that now are available, the ASI Air and some other pieces of equipment aren't very expensive, really help out doing this astrophotography. And it is one way to try to counter the problems with light pollution, because you can cut through some of that stuff. You can use filters, do narrowband imaging. But there's still a great pleasure, and for those people who haven't done a lot of observing, there's nothing like getting out under the stars and looking. So we're going this summer out to Colorado for a few days, and I'm bringing a 3-inch f5 little cheapy telescope. But the fact is that most of the time we're just going to sit there and stare at the Milky Way.
Oh, wow. I'm so jealous.
Very good. Anybody else have any other questions? Anything, any comments, any other comments?
I have one question, Larry. That was just a fantastic presentation. The probe that was able to sample the asteroid, why is it taking so long to get back here? Does it need kind of a boost to get it back? Why isn't it coming right back?
Well, first of all, you know, it got a big boost when it left the Earth, but it didn't carry so much fuel that it could just shoot itself back. So it has to take kind of a orbital path to get here. And, you know, the asteroid is not that close. It's 2 or 3 times the distance of Mars. So to get it here, and to get it here so it's coming in at the right angle and the right speed, and that they can brake it properly to slow it down so it doesn't crash, it takes a little time.
Okay.
To do it right.
I think it's actually making 2 orbits of the sun before it gets back to the Earth. That's why, you know, you're looking at a couple of years before it gets back. Yeah. But they're going to park it in somebody's backyard, you know.
Well, I think it's going to be landed in western Utah, I think, right?
In Utah, yes. Yeah.
Because if you've ever been to Salt Lake, you know that there's Salt Lake City, there's the lake, and then there's like 1,000 miles of like nothing. So.
But if they can go out to Pluto with New Horizons and be within 60 miles of where they wanted to be, this will be a piece of cake.
Oh, it's pretty good that they really can get this stuff to work. I mean, look at the Perseverance, the way that landed, and the Chinese did it just you know, a couple of months later. So the technology is really working well. We have to hope that the Webb unfolds itself. You know, that's a really complicated thing that it has to do. And it's been delayed, and they still had some problems the last time they tried to unfurl it. But I think they say now that it's working. It's supposed to go up in October, and it's supposed to be a 5-year mission. So it's a huge amount of investment, you know, just for 5 years of data. But if they can get it up and it does what it's supposed to do, they'll be able to see population 3 stars, which are the earliest stars in the universe.